minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff of Falcon 9.
This is one of the Falcon 9 rockets, designed by SpaceX to take satellites to space. The creation of these giant rockets is a spectacular feat of engineering. As a rocket scientist in training, I'm working on my own engineering feat. My challenge, though, isn't creating a giant rocket. It's creating a very small one. I'm using many of the same rocket science principles used by SpaceX and NASA to design tiny rockets, like these, to go on board small satellites called CubeSats. These satellites are typically no larger than a loaf of bread. And to get to space, they have to hitch a ride on board one of the large rockets I just showed you. The problem is, CubeSats are so small, they don't have room for a conventional propulsion system. Many don't have the capability to make large orbital movements at all. So when their missions are complete, they remain in orbit as space junk. While space may seem like an endless, infinite expanse, the fact is, the space around our Earth just isn't as big as we used to think. It's been estimated that over 750,000 man-made objects are currently in orbit. When we don't have control over some of those objects, like CubeSats, collisions occur. The crashes damage good satellites, including the International Space Station, and can create thousands of pieces of additional debris. Garbage. Satellite launches have been delayed, and the entire space station has been moved just to avoid small pieces of debris. If things get bad enough, we won't be able to launch anything from Earth at all. I believe that this very big problem can begin to be tackled with a very small solution: tiny 3D printed rockets. Crashes caused by CubeSats could be avoided if the satellites had a propulsion system to move them out of the way of impending collisions, or even to push them out of orbit where they can burn up in the atmosphere. I've been working to design and test different hybrid rocket motors for this purpose. In order to make them work for CubeSats, I need to reduce the rocket's weight and size while following a set of standards used by the CubeSat community. The rockets we use are uniquely suited to this purpose because they're made primarily out of 3D printed plastics. The plastics are non-hazardous, so we can print the rocket fuel right on our desks and test the rockets on campus. This lets us print the rockets into all sorts of weird shapes and quickly investigate the effects of design changes. Most rockets are cylindrical, like these. But in what would otherwise be wasted space in the CubeSat corners and edges, I can instead 3D print complex pathways for wiring and plumbing. The ability to 3D print custom parts on demand is a luxury that the developers of the space shuttle rockets didn't have. It's allowed me and the rest of the industry to dream up bigger and better solutions, or in my case, smaller solutions. This is one of the 3D printed rockets that will go on the CubeSat propulsion system. Now, SpaceX and NASA have had their successes, and they've also had their share of failures. And so have I. In an attempt to maximize the space, my first designs for rockets were completely triangular. They looked great on paper, but when I pressure tested the rockets, they burst at the angular corners. I've had to redesign over and over. And even with the new designs, manufacturing some of these tiny parts has been a big challenge. I've gotten tolerances wrong and had to get creative to make parts fit. I've broken or damaged an unmentionable number of tools, and I get my hands very, very dirty. But it's all worth it for exciting results like this. Testing these rockets in my lab can give me some insights into how they'll work on CubeSats. But in order to research how they'll actually perform in space, I need to do some tests in a vacuum chamber that simulates the space environment. I was able to perform some of these tests at NASA Marshall Space Flight Center in Alabama this past summer. Working at NASA was incredible. On my drive to the office every morning, I got to pass some of the giant rockets that I've been describing, all while carrying my tiny rockets that could have fit in my pocket. With some hard work, we were able to get the rocket test stand designed and built inside the vacuum chamber. When the day of our first test arrived, I watched as the control software notified me that the rocket was sparking, the oxidizer valve opened, a soft roar reached my ears, and I knew the test was successful. This is a video taken through the viewing port of the test chamber. Now, again, this success was not without some struggles. I almost set fire to the NASA building. We had decided to do a second test on the rocket, and at first, everything seemed normal. But then we heard a weird noise. And unusual noises are not something you want to hear when you're doing a rocket test. We quickly discovered that there were flames shooting out the side of our rocket, and our test stand was beginning to melt and burn. My professor quickly put out the fire with a fire extinguisher, and there was very little loss of equipment. But as you might imagine, NASA was not very pleased with us. And that's because I'm not the only one using that building. It housed other spaceflight equipment and experiments, including some of those for the mission to Mars. It reminded me that successful spaceflight is not a one-person job. And developing new technology isn't always an easy path. I'm still striving to find a rocket design that fulfills all of my goals. CubeSats are a small part of the larger debris problem, and my CubeSat rockets are just a small part of the larger space debris mitigation solution. Cleaning up space and keeping it that way is going to take effort from many more people like me. It's going to take consideration from every space agency and private company, from those developing the large launch rockets, down to the designers of each individual satellite. They need to consider what's going to happen to their satellite after its mission is over. They should aim for reducing space debris with every rocket and satellite launched. And with enough small steps, we can take a giant leap, eliminating space debris, so that space stays accessible for everyone seeking to use that stellar resource.